As I drop this tea bag into this glass of hot water, initially concentrated, the tea gradually spreads out, evenly coloring the water. Most text-to-image generation models use diffusion models that aim to undo this process. They reconstruct the original concentrated form from the diffused state. It's like a magic trick, gathering the spread out tea back into the tea bag. Their mission? To take the blurry, diffused image and reconstruct the sharp, clear original, piece by piece. Pretty neat, right? Hi, I'm Jonathan Fernandez, a generative AI expert and co-founder of AIBootcamp.uk. So join me as we learn how text-to-image generation works. Let's take a look at what diffusion is all about. So we start off with an image and let's call it X0. And we add a bit of noise to it, meaning we make it a little more pixelated. And so we'll end up with image X1. Now you might have noticed that there's this bell curve. And what this means is that we're adding noise from the bell curve or the normal distribution. And we'll talk a little bit more about this later. And we keep going. In fact, the first diffusion model did this 1,000 times. And so we'll end up with a fully noisy image or a fully pixelated image. Now that's the easy bit. What we'd really like to do is to go back, and that seems much harder. So the high-level idea of diffusion models is that they receive these images blurred with noise, and they learn to denoise them, outputting a clear image. Now, this is the important bit. Every step we add noise, we also learn the reverse diffusion process. And the way we do this is by training a machine learning model that takes in as input the noisy image and predicts the noise that's been added to it. But because we know how much noise we've added, the model can compare the two and get good at learning to predict how much noise was added. And so it can be used to remove noise from images. Let's take a look at an example. So we're going to be using Google Colab as our coding environment. Now there's a couple of things you need to remember. So the first important thing is you need to head over to runtime and you need to select change runtime type and make sure that you have a T4 GPU or better. Now, what's really nice about Google Colab is that you get a T4 GPU for free. And you can see that we're installing a whole load of Python packages. Now, don't worry if you are not aware of these packages. We'll get into the details of them later. Now, Hugging Face is a company that provides a repository that allows you to store your models. And they've also created several of these useful Python libraries. And so we're going to be using a couple of them. So datasets is from Hugging Face, as is the Transformers library and so on. And the focus of our time together is going to be the diffusers library that allows us to work with diffusion models. Now, in order for you to be able to run the Python code, what you need to do is you need to head over to the play icon over on the left and just hit run cell. Great. Now we know that this cell has finished running because we can see this green check mark. And so let's head over to the next cell. So what we're going to want to do next is we're going to import a whole load of the different libraries. So we installed data sets, we installed diffusion and so on. And so we're going to go ahead and import them so that we can use them. Now, the first line is an important one because what we're saying here is we want to be able to use the GPU rather than the CPU when running this notebook. Now, the model that we're using here is one trained by Google. And what this does is it generates celebrity faces. So the 256 is because each image that's generated is 256 pixels by 256 pixels. So that's the height and the width. Now, DDPM is going to be one of the first diffusion pipelines that we're going to be using. And we're going to store our generated image and be able to view it. So let's go ahead and run this cell. So what's happening over here is that we're going to be downloading a couple of images. And you'll notice that the generation is taking place over 1,000 steps. And so the diffusion pipeline has to go through these 1,000 steps to generate the final image. So this is quite remarkable. Our diffusion model has started off with a noisy image and generated an image of a celebrity. Let's just take a look at the details of the image that's been generated. So what we're doing over here is we're taking the image and converting it to a type of torch tensor. And as we said earlier, the size of the image that's generated is 256 by 256. Now, the 3 corresponds to the fact that there are 3 channels in this image, and these channels correspond to RGB, and this is why this is a color image. All right, so we've seen the high-level idea of diffusion models is that they're able to receive blurred images with noise and learn how to denoise them, outputting a clear image at inference time. Let's take a look at the inputs to the model. So the time step is important to cue the model with how noisy the input image is. It's more noisy in the beginning of the process and less noisy at the end. So the model knows if it's closer to the start or the end of the diffusion process. So this is the input to a black box, which holds the machine learning model. And we then have the output, which is the prediction of the amount of noise added. So what's in this black box? Well, there are 2 things. The scheduler, so this isn't your typical model that has trainable weights. It uses a step method to compute slightly less noisy images. And you've also got something known as the UNet 2D model, which does have trainable weights. Let's head over to our Colab notebook to look at this in code. So what I have here is a helper function, and that's called show images and display sample. So our first line is the model that we're going to be using. So that's the UNet 2D model that I spoke about a few minutes ago. And then we're also going to be using the scheduler. Now in diffusers, adding noise is handled by the scheduler, which means it only requires 50 steps instead of 1000. Let's take a look at the time steps. And so what we do is we give these time steps to the scheduler, and it tells us how to move from one time step to the next, given the model predictions. Now, anytime you want to know a little bit more about a method, you can just go ahead and put a question mark at the end of it. So this is the torch.randomn method. And let's take a quick look at this. So this returns a tensor filled with random numbers from a normal distribution. And we're using this because we want to create a random image from the normal or the Gaussian distribution. And so this is creating an image which is of size 256 by 256. The 3 corresponds to the number of channels. And we've got a 1 because this is a batch of 1 image. So let's take a look at what this noisy image that we've created looks like. And you can see that this is a fully pixelated image. Now what we'll do is we'll go through this step by step, and then we'll put this all together in a loop at the end. So what we're doing here is we're passing this through the model to predict how much noise is. And then we also want to pass the time step so that the model knows at which point we're at. Now the scheduler output will tell us what the updated image should look like. Then we can go ahead and see a slightly less pixelated image. And if we go ahead and combine all of the steps from earlier, and you can see that this is step 10, step 20, all the way up to step 50. And you can see that this is progressively becoming a less and less pixelated image. And finally, you'll notice that this looks a lot like a celebrity face. This is because there are 2 kinds of diffusion models, unconditional and conditional. Unconditional diffusion models are ones where they don't have any additional input. So if you train these models on a set of images that are just celebrity faces, then it will only generate images that look like celebrity faces. It won't be able to generate images of flowers or houses and so on. With conditional diffusion, you are guiding the model based on something else, like text. And here the training data would include both the images and some associated text about the image. So this is how the model is able to generate images based on text. And this is how most text-to-image generation models work, like DALL-E 3, Midjourney, and Stable Diffusion. All right, so there are conditional and unconditional diffusion models. Unconditional generate images that look like the data that they're trained on, and conditional diffusion models are additionally guided by something else, like text, to generate the images. And finally, the UNet models that we've seen here are just trying to predict the amount of noise added. This video has a little bit of mathematics, but stay with me. It's worth it because later when we look at the relevant code, the variable names will make sense. I promise I'll keep it high level and accessible. So we move from one time step image to the next by adding some random noise, and that's called epsilon, which looks like this letter E. Now, remember when we talked about that earlier? For each single noise step going from time step t minus 1 to time step t, we'll be adding some Gaussian noise. So by Gaussian, we mean that the random noise just follows the classic bell curve distribution. Now, we want to control how much noise we can add to the image, and so we call that beta, and it looks like the big letter B, and it's defined for each time step, and it tells us how much noise should be mixed in that step. So in other words, the new image we get is a combination of the previous image and some random noise with the amount of noise scaled by this beta value. Now, what's nice is that we can go further and define this as a distribution and that it's part of the Gaussian or Bell distribution. Now, the reason that this is helpful is that if I want to add some noise to the previous step's image, it's not just some random amount. Instead, it's likely to be close to what you had in the previous step with some amount of randomness that's described by a bell-shaped curve. Now, because the bell curves all look pretty much the same, all you have to do is define two things. The mean, which is the center of the bell curve, and that's given by the 1 minus beta t and so on, and the variance, which is given by beta t, which is how spread out things are from the average value. Now, that's pretty much all the mathematics we need to cover. So the bell curve is also called the normal distribution, which is why we have that symbol that looks like a stylish N. So all this is saying is that if I want to figure out the probability of how much noise to add, then given only the previous step's image, I would need to add noise given by the Bell distribution that has this center and this variance. So let's go ahead and confirm some of this in code. Now I'm just going to go ahead and install some of the libraries in case your Colab notebook has timed out. Now here from the Hugging Face hub, we're going to use a collection of 1,000 butterfly pictures. And so you can see that the image size is going to be 32 pixels. The batch size is going to be 64. And then what we're going to do is we're going to pre-process the data set. So we're going to go ahead and resize it. And so we're going to resize the images in this butterfly data set so that they're of size 32 by 32. And then we're going to convert them to a torch tensor. And then we need to normalize them. And so what we mean by that is we want them to have the values between -1 and 1. We'll have a transform function where we can apply the pre-processing that we defined earlier to the images. And so the pre-processing has taken place in this step here. And then finally, we'll want a data loader. And the purpose of the data loader is to serve the images in batches. So let's take a look at a batch of 8 images. And so I'm going to go ahead and run this cell. And so these are 8 images of butterflies from this data set. Now let's define our noise scheduler, which is going to be using the DDPM scheduler. That means it's going to have 1,000 steps. And you should be able to recognize some of the values from this noise scheduler. So for example, we've got these beta values. So that's beta end, beta start, and the beta schedule. And we saw this earlier because we use beta to scale the amount of noise. Now, when it comes to setting up a good noise scheduler for your model, it's all about striking the right balance. So you want your model to see a nice mix of images with different noise levels during the training. So the ideal setup will depend on the specific data you're working with. So on this first line, we're defining a low beta end value. And you'll see that if the beta end value is too low, your model never gets exposed to images that are completely corrupted by noise. So the blue line corresponds to the component of the original image, and the orange line is the component of noise. Then you can see that we've got this gap over here, meaning that the images aren't completely corrupted by the noise. Now that's not ideal because during the actual inference process, the model starts from a state of pure random noise, so it needs to learn how to handle that level of noise during training. Now, on the flip side, if you crank up the beta end way too high, so we've got 0.05 over here, and let's go ahead and scroll down and see what these look like, then most of the training steps will be spent on images that are almost entirely noise. You can see over here from step 400 onwards, most of the image is completely noise. And this is going to hurt your model's performance because it's not getting enough exposure to less noisy images. Now let's experiment with different beta schedules. So different beta schedules will give you different noise curves. And let's take a look at the cosine scheduler. The cosine scheduler is a popular choice because it provides a smooth transition from the original image all the way to pure noise. All right, so the main takeaway from this section is that we can move from one image to the next step by adding some noise. It's not just some random amount, instead it's likely to be close to what you had in the previous step with some amount of randomness that's described by the bell-shaped curve. And by varying the amount of noise by using different beta values and schedules, we can train a model that can learn how to predict how much noise has been added to an image. Okay, let's talk about the star of the show, which is the model that makes all these important predictions. So this model needs to be able to take in a noisy image and output its noise. So this allows us to denoise the input image. But we need a model that can handle images of any size and output an image of the same size. Now, it's not just about the size. The model needs to be able to make pixel level predictions while understanding the bigger picture of the image. And so a popular approach for this is what's known as the UNet architecture. And UNets were originally invented in 2015 for medical image segmentation, but they've since become a go-to choice for various image-related tasks. So let's talk about how UNets are structured. So they're essentially made up of two main components, downsampling blocks and upsampling blocks. So the downsampling blocks are the ones that take care of reducing the image size, and they usually have a couple of convolutional layers followed by pooling layers or downsampling layers, which helps to shrink the image down. Now, these convolution layers and pooling layers are common layers that you'd find in image models. And then you've got the upsampling blocks, which do the opposite. They increase the image size, and these blocks typically have convolution layers followed by upsampling layers, which helps to expand the image out. Okay, now let's talk about what makes UNets really special. It's about these skip connections that connect the downsampling and the upsampling blocks. Basically, these skip connections act as a direct pathway for information to flow from the downsampling blocks to the upsampling blocks. This allows the model to make super precise predictions at the pixel level while also understanding the overall context of the image. It's like having the best of both worlds. So let's go ahead and see what this UNet model looks like in code. Now, this is the definition of the UNet model. So, for example, this sample size is a reference to the target image resolution. And then the number of input and output channels is the three channels that we've looked at. So that's RGB for color images. The layer blocks is how many ResNet layers that you'll need per UNet block. And here in the down block 2D, this is your regular ResNet downsampling block. You'll notice that the other two blocks are different. And this is a ResNet downsampling block, but it also has something known as self-attention. And you can see that we've got a mirror reflection for the upsampling blocks. So let me just go ahead and run this code cell. Now, because we're using Hugging Face's Diffuses library, let's talk about some improvements that have been made to the UNet. So you can see we've also got layers like normalization. And this helps the model learn more quickly and reliably by ensuring the outputs of each layer are centered around 0 and have a standard deviation of 1. And then you've also got the dropout layers. And dropout helps prevent overfitting the model to the training data. So this is important when we're working with small data sets. Now, further down, we've got the attention blocks. And so it's this section over here. And this self-attention mechanism allows the model to concentrate on different parts of the image at different times. And this can help the UNet learn more complex functions. So it's like having a super focused eye that can zoom in on specific details as they're required. So let's say you're trying to generate an image for a garden. The self-attention layers might focus on the flowers first and then capture their details and then shift the attention to the leaves and so on. So this way, the models can build a pretty comprehensive understanding of the scene. Now, adding these transformer-like attention layers also gives us the ability to increase the number of learnable parameters. And so this can lead to better performances. But there's a catch because these attention layers are very expensive computationally, and they're more expensive than your regular convolution layers, especially at higher resolutions. So what we normally do is you'll use them only at lower resolutions, like in the lower resolution blocks of the UNet. And this is basically a trade-off between the performance and efficiency. Then you can see that we've got our noisy batch of 8 images. And we're going to go ahead and see a prediction from the model. Now, what we'll want to check and confirm is that the UNet's input images are the same as the output images. And that's why we have this assert function over here. And that is, in fact, the case. All right, so we've taken a look at the UNet model, and we can see that this is a great model because it allows us to handle images of multiple sizes. But not only that, the model is also able to make pixel level predictions while understanding the big picture of the image. Let's take a look at what's involved in training a diffusion model. Now, if you've trained a machine learning model before, you'll be very familiar with this workflow. Now, remember, we want the model to do a really good job of estimating how to denoise images that are close to perfect and have no noise, and also those that are extremely noisy. So we want a data set with diverse amounts of noise. So these are the steps that are involved. So what you'll want to do is to load your training image from your data set. You'll then want to add varying noise levels for diverse denoising tasks. Then comes input the noisy images to the model. And then you'll want to evaluate the model's denoising performance. And then finally, you'll want to update the model weights based on your evaluation. Let's go ahead and install the libraries in case your Colab session is timed out. And we go ahead and define our model. And so this is the UNet model. And let's work our way through each of the different sections before we build that up into a for loop. So this is our data set, which is the butterfly data set. Now this is our noise scheduler. And so we'll have a batch of images, and the batch is going to be of size 64 with these images of size 32 by 32 and 3 channels. And our clean images are going to be of exactly the same size. Now we want to be able to sample the noise to add to the images. And so we can use the torch rand_n, which will give us the batch size that we want. And now we want to be able to sample a random time step for each of these images. We then want to add noise to the clean images according to how much noise there is at each time step. We then use our model to make a noise prediction. We can then determine the loss, and then we can go ahead and do backpropagation, and then we can keep a track of the values of the loss to determine and ensure that our model is improving. So let's go ahead and confirm a learning rate and the optimizer that we're going to be using, which is the Adam optimizer. And again, this is all standard practice if you're familiar with training a machine learning model. And we're going to train this for 20 epochs. Now, we're only going to train it for a few number of epochs because this is a small data set and we don't want to take too long. And let's go ahead and train this diffusion model. Now, what we'll want to be looking out for is that there's a downward trend for the loss values. And this means that our model is improving as it's being trained per epoch. Now, we really should be training our model for significantly longer. You can see that this is now finished training. Now, just for the sake of time, I've trained it only for 20 epochs. So what we should see here then is that we've got an image that's generated that should look remotely like a butterfly. Because this image is only going to be 32 pixels by 32 pixels, it's going to be very small. So I'm going to have to zoom in to take a look at what this looks like. So you can see that it's going to run through the 1000 steps and it's going to generate what hopefully looks like a butterfly. And that certainly looks like a butterfly. I'm just going to go ahead and try and zoom in here. And I think you'll agree with me that that does look like a butterfly. Now, if you wanted to get a slightly better picture, you'd probably want to train for a little longer. So now that we've trained this model, let's go ahead and save it. And we can take a look at the different components as they're saved by the Hugging Face diffusers library. So we've got the scheduler, the unit, and the model index. So if we take a look at the model index first, this gives us information about the diffusers library that we've saved. And you can see that we're using version 0.25 of the diffusers library. I can then take a look at the unit model. And so here you can see these are the weights of the unit model over here. We can also take a look at the configuration for the unit model. So this will give us information about the down blocks and the up blocks and so on. And we can get details about the scheduler in the scheduler config file. And you can see, for example, the beta start and the beta end values and so on. All right, so you can head over to the Hugging Face hub and see if there are any other data set that you'd like to train your diffusion model on. Now, make sure that you keep the image sizes small so that the training times and the compute requirements aren't significant. Now that we've trained our model, how do we know it's any good? You know, judging how good these AI-generated images are is pretty tricky. I mean, it's quite a subjective thing. A common approach is to have people look at it and rate the images themselves, but also use quantitative metrics to evaluate them more objectively. So these metrics provide a standard way to assess quality, even if they don't always line up perfectly with what looks good to a human eye. The fresh ray inception distance, or FID score, is a way to measure how similar two sets of images are. So imagine you're working on a project where you need to create artificial images that look like real photographs of butterflies, and you want to know how well your project's doing. So are the artificial butterfly images realistic enough? That's where the FID score comes in. So let me give you a simple analogy. So think of the first set of images as artwork made by a famous artist. So these are the real photographs of butterflies. And the second set as an artwork made by you, which are the artificial images. You want to see if your artwork can pass off as the famous artist's work. Now, to compare the two sets of artwork, we call in an art inspector. And this inspector is really good at examining art and understanding different styles and details. In the world of FID, this inspector is actually a model known as the inception model, trained to look at lots of different images and understand their details. So the art inspector takes a look through the two galleries, one displaying the famous artist's work and the other displaying yours. And as they walk, they take notes on various features of the artwork, such as the colors and textures and shapes and so on. And this is like the inception model, looking at both the real and the artificial images and analyzing their features. And then after the walk, the art inspector compares notes taken from both galleries. So if your artwork's features are very similar to those of the famous artists, then the notes will be quite alike. So in FID terms, this is where the scoring takes place. The model uses a special formula to calculate the distance between the features of both sets and images. So a smaller distance means a lower score, and the images are very similar, indicating your artificial images are quite realistic. But there are some limitations to the FID scores. So they're designed to compare two different distributions or groups of data. So to calculate an FID score, you need to have access to both the source data set so that you can compare against them. Now, one thing to keep in mind is that you can't calculate the FID score for just a single image generation. You need to have a whole batch of generated images to compare against the source data set. And when comparing FID scores, the images are usually resized to 299 by 299 pixels. So this means the FID might not be the best metric for extremely low or high resolution images. It's also worth noting that the FID scores can be quite sensitive to various factors. For example, changing the number of inference steps or the scheduler used during the generation process can lead to very different FID scores. And so you'll need to be careful when making comparisons. So FID scores are a handy way to compare distributions of generated images, but you need to be mindful of the various factors that can influence the score and make sure you're using consistent settings when making comparisons. We can also guide our model to generate specific types of images. And this is called conditioning, where we essentially ask the model to create an image belonging to a predefined category rather than just any random image. Conditioning is actually pretty straightforward, but it's a really powerful concept. So we'll start with the same diffusion model we used earlier, but with a couple of tweaks. So instead of the butterflies dataset, we're going to use the fashion MNIST dataset, which contains thousands of clothing images across 10 different classes. Now, there are a couple of things you'll want to notice about the fashion MNIST dataset. Firstly, the images are of size 28 by 28 and not the 32 by 32 that we've used before. And secondly, you'll notice that the images are grayscale images and not color. So there are two considerations there. One is thinking about the size, and the second thing is to think about the number of channels that we're going to be using. Let's take a look at the labels available within the fashion MNIST dataset. So label 0 corresponds to a t-shirt, 1 corresponds to a trouser, and so on. Now, this is the crucial part. We're going to feed in two inputs into the model simultaneously. We're not just showing it examples of real images, but we're also telling it which class each image belongs to. So with this approach, we can expect the model to learn how to associate images with their respective labels and to grasp the distinct visual features of, for example, t-shirts and trousers and so on. So let's head over to our notebook. So we're going to pull down the fashion MNIST dataset. And there are a couple of important things to note about our pre-processing. So firstly, we're going to go ahead and pad our 28 by 28 pixel images. And so we're going to pad them with 2 pixels. So think of this like having the 28 by 28 pixel images and then with a 2 pixel border. The next thing we'll have to do is we need to make some changes to our model. So now the input channels are no longer 3, but 1. And we're also going to specify that the number of class embeddings are going to be 10. And these correspond to the 10 classes available with the fashion MNIST dataset. We then have our scheduler. And you can see that we're able to add a noise to the first class of the images. And let's go ahead and train our model. So this time we're only going to use 3 epochs. And again, this is just so that the training time doesn't take too long. And let's take a look at what's part of our training loop. So we're going to go ahead and load both the input images and the classes. And then like before, we're going to add noise to the images. We're going to sample a random time step for each image. We're going to go ahead and add noise. We're going to go ahead and get the prediction from the model. We then compare the prediction with the actual noise, and then we can add these values to the losses. We do a back propagation, and then we update the model weights using the optimizer. So let's kick off this training run. Now, this training run should take anywhere between 5 and 10 minutes. Okay, so we've gone and trained our model for 3 epochs. Now, let's see how well our model does. So what I'm doing is I've got a function called generate from dataset, and I can submit any of the classes here. So for example, in the fashion MNIST dataset, I've got label 0 all the way to 9. So if I submit label 0, for example, I would expect to see images of t-shirts. And you can see that these are pretty good representations of t-shirts. Now, again, we've only just trained it for 3 epochs. If you want to be able to see better results, then we'd want to train our model for more epochs. If you want, go ahead and pause the video here and provide some other classes for the model to generate. So if you want, you can generate sneakers and give it a value of 7. So let me show you how that would work. So you've got class to generate is 7. And let's see how the model does. Now you can see that the images over at the right certainly look like sneakers. The first couple of images are a little bit more difficult to see. So with conditioned models, we're not just showing it examples of real images, but we're also telling it which class each image belongs to. Now for this challenge, we're going to continue looking at conditioned diffusion models, but we're going to be looking at the CFAR10 dataset. And the CFAR10 dataset looks something like this. So we've got 10 different classes: airplane, automobiles, birds, cats, and so on. Now, if you head over to the notebook, you can see that you've been provided a link where you can actually go ahead and download the dataset. So go ahead and try and see what changes you need to make in order for you to be able to generate images from the CFAR10 dataset. Let's go ahead and look at the solution. Now we're going to use the Fashion MNIST dataset code as our starting point. So we just want to make sure that we have the libraries running. And we've got the CFAR10 dataset over here. Now, the important thing to notice is that the CFAR10 dataset has 32 pixels by 32 pixels. So there's no need for us to pad it. So we can just go ahead and comment out the pad pre-processing that takes place here. And what we'll also want to check is what format the dataset's available in. So if I go ahead and just run CFAR10, you can see that when it's available in the Hugging Face dataset, the features are known as IMG and label and not images. So the only change we'll need to make over here is we can replace images with IMG here, and we're fine with label over here. And so this should do the trick. Now we'll need to make changes to the model. And so our UNet2 model will need to have an in channel of 3 because this is an RGB image. And similarly, the out channel will need to be 3. And there's no change to the number of classes because the CFAR10 dataset also has 10 classes. And finally, the only other change we'll need to make is the number of channels over here. Then you can see that this image of a deer is being progressively pixelated. And the deer is one of the classes in the CFAR10 dataset. So like with the Fashion MNIST dataset, we're going to just train for 3 epochs. And this is just for the sake of time. And so this should take anywhere between 5 and 10 minutes. And again, we've just trained for 3 epochs. Now let's go ahead and just pull up the CFAR10 dataset. Let's pick a category. So I think the ship category is going to be quite a unique one. So we just need to use the label 8 here. So perhaps let's try airplane first, which is 0 and then 8, just to see how well our model does. So we need to make a change to our generate dataset also here. And so let me go ahead and change that to 3. And that's because the CFAR10 has 3 channels as opposed to 1. So we're now generating an image from class 7. And so let's go ahead and use class 0, which is airplanes, and see whether we get images that look like airplanes. Now, regardless of which label I try, it's much more difficult to be able to distinguish things with the CFAR10 dataset versus the Fashion MNIST dataset. The best results that I got were trying with the class 6, which corresponds to a frog. And so let's go ahead and try that. And it looks like the only way around this is to be able to train your model for a couple more epochs. So if you're looking at perhaps more than 10 epochs, then you might be able to get better results. Now, you can just about make out the legs of the frogs over here and over here. But again, because the CFAR10 images are pretty small in any case, it's quite a difficult task. All right, so the big takeaway from this is we're able to incorporate the labels as part of the information that we're sending to the model. And in this case, there are three things we need to be cognizant of. So one is the size of the images. The second thing is the number of channels. And finally, the number of classes. Okay, so we've got this conditional model working now, but before we get too excited about text-to-image generation, we need to talk about scalability, because as images get larger, the computational required gets incredibly expensive, particularly for self-attention. So far we've been working on images that are tiny. They've only been 32 pixels by 32 pixels. A 128 pixel image is 4 times as large, but will require 16 times the memory and compute in a self-attention layer. Now imagine you have a photo that's just too large to work with. Well, latent diffusion has this trick to solve this. It uses a separate model called a variational autoencoder. And these models can compress your images down to a much smaller size while still keeping all the important details intact. So it does this by taking your 3-channel color image and it produces a 4-channel latent representation. So at the same time, it can shrink each dimension by a factor of 8. So a color 512 by 512 pixel image would have a total of 786,432 values. With the variational autoencoder or VAE, each dimension gets reduced by a factor of 8, so 512 becomes 64. This means we're now only working with 4 times 64 times 64, which is 12,288 values. Let's confirm this in code. So I'm going to pull down a photo of a boat that I took. And you can see that this is a 512 by 512 pixel image that's been resized to these dimensions. And we want to go from this image to a 1 by 4 by 64 by 64. So this is the current shape of our image with the 3 channels. We can go ahead and include an additional channel at the start. And the reason that we need this additional channel is because we'll treat this single latent in a batch. Now, if we take a look at the VAE config, we can see the down encoder and the up encoder blocks. And in addition to this, we can see what's known as the scaling factor. And this scaling factor is what the researchers used for the stable diffusion model. So let's go ahead and encode our image. And you can see that it's now 1 by 4 by 64 by 64. And let's take a look at the 4 channels. And so this is the same image with the boat across the 4 channels. Now let's do the reverse operation, which is where we take the latents and go back to the images. And you can see we're getting back our image with the boat. And this isn't very different from the original input image. In fact, go ahead and pause this video and compare the quality of these 2 images. So this is brilliant because instead of working with the full-size images right from the start, you can first process smaller, condensed versions of the images called these latent representations. And by doing this, the diffusion process on these smaller representations, they get a lot of the benefits that come with using small images, like using less memory, needing fewer layers in the neural network, and faster generation times. And so this is the best part because once we're done with all the processing, we can still decode the results back to a high resolution image when they're ready. The benefit you get here is that you don't need massive amounts of compute to run these models. So you can now use commodity GPUs, and that's exactly what happened. The teams from Runway ML, Lion, and Stability AI partnered together, and the result of this was Stable Diffusion, a text-to-image model that could run on end-user GPUs. We'll take a look at text encoders, which is an essential part of being able to generate images from text next. Remember when we talked about how the UNet can use additional information to control the image generation process? We then use the Fashionamnist dataset and passed the labels as one of the channels so that the model generated that class of images. Well, with text-to-image models, the additional information is the text prompt you provide. So let's say you want to generate boat on the sea. you'd feed that description along with some random noise into the model. And then the model then tries to transform that noise into an image that matches your text prompt, boat on the sea. But for this whole text to image thing to work, the model needs some way to understand the text prompt, right? That's where the text encoder comes in. It takes in the words you typed, like boat on the sea, and turns it into a numeric representation that captures what these words are describing. It then feeds these numeric embeddings into the UNet model, along with some random noise and other data, and the model can then generate an image matching your description. So this is where CLIP comes in. So the CLIP model was developed by the team at OpenAI, and so we're over at the OpenAI website. Now, CLIP, or to give it its full name, Contrastive Language Image Pre-training, is a deep learning model that excels at understanding the relationship between text and images. It's trained on these image-text pairs where the text descriptions act as labels for the images. And this allows CLIP to grasp a wide range of visual concepts. So CLIP possesses these two key parts, an image encoder and a text encoder. And these encoders transform both images and text descriptions into a common space. And by analyzing the similarities of these encoded representations, CLIP can determine how well an image and its descriptions match. So, contrastive language image pre-training, or CLIP, sounds like quite a mouthful, but it's not that complicated. What this means is that CLIP uses contrastive loss for when it was trained. So this forces the model to identify similarities between matched image text pairs while pushing apart unmatched pairs. So as an example, if you were to train a model so that the image of a cat and the word cat are close to each other in vector space, both of these would also be relatively close to, for example, the word dog, but far away from, say, the word boat or images of a boat. Now, because CLIP is specifically trained to understand the relationship between text and images, you can then just use the text encoder to help with making sense of text data that is submitted to the UNet. But these encoder models don't understand words, they understand numbers, and so we need to convert this text into a sequence of numbers using a process known as tokenization. So it looks something like this. If you were to take in the word boat on the sea and send it to the model, it first needs to be tokenized. And so boat on the sea is split out into separate tokens. And we then have two new tokens, a token at the start of the text and a token at the end of the text. And these tokens have numbers that they are mapped to. And token embeddings capture the meaning of the words, and they capture the order or position of each token using positional embeddings. And so this can then pass through the 12 layers of the CLIP encoder model. All right, so we've got this excellent model that excels at understanding the relationship between text and images. And in the next video, we'll confirm our understanding of this in code. Now, the CLIP model is supposed to have an excellent understanding of the relationship between text and images. So let's confirm that's the case in code. So what I'm going to do is I'm going to go ahead and grab the image that I had, which is the image of a boat on the sea. And let's pull the CLIP model from Hugging Face. And so this was made available by OpenAI. And so what we have here is both the model and the tokenizer. Now, the test that I have is I'm going to provide two texts, a photo of a boat and a photo of a dolphin. And I want to send these both to the CLIP tokenizer along with my image and see which of these two texts is more closely aligned with the image that I have here. And clearly this is a photo of a boat and not a photo of a dolphin. So if I send this to the tokenizer, you can see that this is the output from the tokenizer. And let's submit that to the CLIP model. And if I go ahead and scroll at the top, you can see that I've got these logits per image. And so if I go ahead and take a look at the logits per image, now what I'll want to do is to use PyTorch's softmax function to allow me to confirm which of these two is more closely related to the image. And I can use the softmax as a proxy for probability that will allow me to confirm this. So I've got the first one as a photo of a boat and the second text as a photo of a dolphin. So let's go ahead and confirm this. You can see that what the softmax function is saying is that the first text, so that's a photo of a boat, is more closely aligned to that image by a margin of 98 to 2. So now that we have our clip tokenizer, let's check out the vocabulary size. And you can see that the vocabulary size for clip is 49,408. And you can also get the mapping between the vocabulary and the tokens. Now, if you want to be able to see the special tokens, you can see we've got the beginning of sentence and end of sentence and unknown tokens and so on. So the beginning of sentence token ID has value of 49,406 and the end of sentence and padding have the same values. So if I was to take the text boat on the sea and send that to the clip tokenizer, this has then been tokenized to boat on the sea as we saw in the last video. And so I can then take the tokenizer and we can get a better view of the layers within the clip model. Let's take a look at the embedding layers. So we've got the token embeddings, which has 49,408, which corresponds to the vocabulary size of the clip model, and 768 is the number of dimensions. The position embeddings is 77 because this is the maximum input length for clip, and the 768 again is the number of dimensions. So if I was to tokenize the word boat, I get the token ID as 4440 for the boat. I can then go ahead and encode that, and this will correspond to the number of dimensions. And we can see that by using the shape attribute. Now, the 6,768 corresponds to the fact that we have 6 tokens in the sentence boat on the sea, including the beginning and end of sentence. And finally, we can see that the 77 corresponds to the maximum number of input tokens for the clip model. So clip is a very impressive model, understanding the relationship between text and images, and this will be pivotal in us being able to put together our text to image generation model. We're finally there. We've covered all the components that are used in text to image generation, and there's just one thing we need to iron out before we pull it all together. So these models are heavily influenced by the input image rather than the prompt. Now, that's not really what a text to image generation model is supposed to do, because if the model doesn't pay attention to the prompt, the resulting images might not match what we're describing. So classifier-free guidance is a way to try and address that. And it's a technique that combines two types of image generation models, one that can generate images from text prompts, which are conditional, and one that can generate images without any text input. So these are unconditional. And then during training, the model sometimes sees blank text inputs, forcing you to learn how to generate images without any text guidance. Then, when you want to generate an image, the model makes two predictions, one with your text prompt and one without any text input. The difference between these two predictions is used to adjust that final image, pushing it further in the direction indicated by your text prompt. So in a moment, we're going to give the model the prompt boat on the sea, and the model will generate one image based on the prompt and another image without any text guidance. And by comparing the two, it can figure out how to adjust the final image to better match the description. So we've got 4 guidance scales over here, 1, 2, 4, and 12. And let's see how closely aligned they are to the prompt, a boat on the sea. And you can see this first and second one aren't very closely aligned to the prompt. The third one seems to be doing a reasonable job, as is the fourth. So let's put everything together using classifier-free guidance. So we're going to use a guidance scale of 7.5. The height and the width of the images are going to be 512. And then the number of inference steps are going to be 30. We then want to use our tokenizer to tokenize the input. And so we provide our prompt, and our output will be a tokenized string. We want to do the same for our unconditional input, and that's going to be a blank string, as you can see over here. We then want to feed both the text embedding and the unconditioned embedding to our text encoder. And then finally, we're going to concatenate or combine the two sets of text embeddings. So let's go ahead and run this code cell. Now, the next thing we want to do is we want to prepare the random starting latents. And then finally, we want to have our loop. So you want to create two copies of the latents to match the two text embeddings. So that's one that's unconditional and one that's conditional. We then want to predict the noise residual for both sets of input. We do that here. We then want to split the prediction into unconditional and conditional. And then we want to perform the classifier-free guidance over here. And finally, we're able to compute the previous noisy sample. And then our final step is the moment of truth. And this never fails to take my breath away. So we have an image of a boat on the sea, which is 512 pixels by 512 pixels. Although the focus of this course is about how text-to-image generation models work, there are many challenges that you need to be aware of. You know, a big worry with these text-to-image models is the copyright side of things. They're trained on these massive image datasets, which could very well include artwork, photos, and other copyrighted stuff without proper licenses or permissions from the creators. So it raises some tricky legal questions like, are we infringing on artists and photographers' rights by using these models and the images they generate? And at the moment, there are a couple of ongoing lawsuits between model providers and artists, and I can't see this going away anytime soon. And since these models learn from data, any biases or skewed representations in the training datasets can also get captured in images they generate. So if the data lacks diversity or promotes stereotyping, the model outputs might start echoing these stereotypes about different races and genders and ages and so on. Now, as amazing as photorealistic text-to-image tools are from a technological standpoint, they do open up some troubling possibilities. Bad actors might try exploiting them to manufacture deepfakes or misleading imagery to push their agendas, anything from propaganda and defamation to inciting violence. Now, it could potentially violate people's privacy by generating pictures of them without consent. So imagine if it made an image of you that a company then used in an ad campaign. And finally, there's the risk that the text-to-image generation models becomes concentrated in the hands of a few powerful companies. This could limit access to the technology, and then who controls the types of images that are generated? It's really important we think through how we can responsibly develop and deploy this technology in a way that minimizes harm and addresses issues like bias. It's very easy to get caught up with how fascinating this whole space is, as we've seen in this course, and overlook the potentially serious challenges and biases that come along with these models. Preparing for these challenges need to be just as much of a priority as understanding the technology itself.